I'll probably skip through a few slides for time, but I'll talk a little bit about CSIRO, or the CFD team, and some of the work we do, the development work of a dry slag granulator that's been going on for a number of years and is now being successfully tested at a large scale, and a little bit about the software features. Who are we? CSIRO is Australia's National Research Science Institute. Our group's across the road there. I'm in Mineral Resources Business Units. We're probably one of the largest groups doing research in mineral processing in the world. And I lead the CFD team. We currently have about 3 full-time staff and a couple of students at different places. Very strong in resource, mineral processing, a whole lot of different areas. Our main focus is really on multi-phase flow, complex physics and multi-physics applications. We do multi-phase reactions, heat transfer, and when I say electromagnetics, I'm talking about MHD type flows. Just a couple of project areas that we've worked on. Flotation cells, doesn't work too well. Flotation cells up the top there, 3-phase gas, liquid, solids. We've done a lot of work in aluminium reduction cells, and some of the models that we've developed and had used in a couple of international aluminium companies. A lot of work in stirred vessels over the years, both gas, barge, slurry vessels, solid hold-up, looking at reactions where you're mixing in acid into systems in autoclaves and that type of thing. Done work in electrowinning for copper and have quite unique experimental system there, a full-scale single cell for generating something like 25 kilos of copper in a production run. Done work on flash smelters, over 28 years I think it is of thickener development through Amira projects. We've done work in erosion, have experimental facilities there where we can measure the erosion using a contact measurement machine to get the profile and the depth, and then we can reduce that in CFD modelling and then link that into a lot of slurry and gas particle systems. Done a lot of work over the years on fluidised bed cokers and other fluidised bed systems. And we have access to a number of other groups in CSIRO, including a state-of-the-art fluid dynamics and laser lab system. The software, well, I guess the group has over 30 years background history applying CFD to multi-phase problems in the minerals industry. Currently our main software tools are ANSYS CFX and ANSYS Fluent. And I guess I should mention there's a couple of other small groups doing CFD in CSIRO, and there's a large group in Data 61 who develop their own code using DEM and SBH, Paul Cleary's group. So the problem I wanted to talk about today was development of a dry slag granulator. There's something like 2 million tonnes of slag generated by the steel industry in Australia and about 200 million tonnes internationally. Comes out at about 1500 degrees C, and as you can see by the picture, they either just dump it and let it cool, or they water granulate it. If you water granulate, you use a lot of water and produce a lot of H2S. If you just leave it and dump it, you've still got to do something with the material and you're losing a lot of heat. CSIRO had a concept that if you drop the molten slag onto a spinning disc, you could produce droplets. If your slag came in at 1500 degrees, you blew air into the system, you could cool those droplets, produce granules of about 2 millimetre size down the bottom that would be crushed up and used into cement, and you might be able to produce reasonably high-grade heat. So that was the concept. A PhD student a number of years ago got it working on basically a 1 kilogram batch scale, but the question really is how do you go from something in the laboratory that a PhD student's got working to something that's going to produce something like 120 tonnes an hour, continuous system. And our strategy was to use CFD to guide, design, solve the problems and do the scale up, working with the experimental groups. So this is the conceptual design. You can see the slag drops in at the top onto the spinning disc. You can see how the disc spins, breaks up into ligaments and droplets. You end up with a whole lot of really hot droplets spinning around in this torus region, then they come out through the bottom. So for us, we sort of broke it up into 3 CFD type problems, if you like. One, looking at the spinning disc, what's going on there. Another one looking at the breakup, and then another problem looking at what happens in the granulator. So the disc model, we used 2D model where we basically have the slag coming in onto a solid disc. The slag spins out. We can then look at the flow, the temperature profile, look at the conjugate heat transfer through the disc, and then predict a solid layer, because the idea for something like this in a lot of metallurgical processes is if you freeze the material you're producing onto whether it's the refractory or onto the disc, you then provide an insulating layer that prevents the disc being melted away or eroded away. So one thing we were very interested in is being able to predict this, the thickness of this slag layer and the temperature on the disc, so the disc would survive in operation. The next area we tried to look at was you had the disc spinning, you have these drops of slag filming onto it, you then get these ligaments that then break up into droplets. So we did a resolved VOF type simulation looking at that, and we were able to do surprisingly well if you compared the CFD drop size prediction with the measurements of the granules produced out of the system. So we were quite happy with that. Then on the granulator, we did a lot of work simulating the granulator where we have air coming in, spinning around, going out through the top, the particles coming off the disc. So that we use the disc model to get an idea of the temperature, the size of the droplets coming off the disc. Then we track those through the granulator, look at how they cool, and look at how they travel through the granulator and then go out through the bottom. And from that, we can get an idea of what the off-gas temperature would be under different conditions. And you can see these are fairly short tapping tests, but we can get a reasonably good idea of what the heat production is so that we can then look at how changes to the geometry, disc speed, tapping, etc. will affect performance, and look at how, as usual, when you're doing something like this, you have to do a number of changes to the prototype design. So we're able to model those to try and help the experimental scientists look at design changes and how to improve performance. As part of the work, we developed at the top there a model for droplet cooling and built that into the particle tracking. So I guess at the end of the day, we used ANSYS CFX to build this. We used a whole lot of different models, single phase fluid flow for the granulator, heat transfer coupled into that. We used a 2-phase VOF model for the disc, looking at the material coming down, flowing across. Used an Eulerian model for the breakup, the droplet breakup, because we wanted to be able to calculate some of the interactions there. We obviously had radiation there and particle tracking, and a little bit of user Fortran to develop a few of the sub-models. So how does that sort of fit into the whole technology development, if you like? Well, originally there was a small system built here, basically a PhD work. You used CFD to go up and build a 1.2 metre system. That was operated and proved successful. Built a 3 metre rig which was operated, able to produce about 5 tonnes an hour. And we've just designed, working with a Chinese engineering company, and they've built a 5 metre rig, and we're currently operating that, or our Chinese partners are currently operating that successfully at about 200 tonnes an hour in China. So that's quite a development over quite a long period of time for quite a complicated process. And hopefully in the next couple of years we'll be able to move into a full-scale commercial unit. I'd just like to thank sort of some of Yuha, Benny and Yuqing have been doing most of the CFD work on the dry slag granulator, and there's a few past and present team members who did did some of the other work there. I'd just like to acknowledge all of those. Thank you.